So when omega 0 is greater than beta, we have both the real part and imaginary part, and this imaginary part is non-zero, so lambda plus and lambda minus are different. Final result for the differential equation should be a linear combination of these two functions, exponential minus beta t e to the I omega prime t, and exponential minus beta t minus e to the minus I omega prime t. If I replace this one with the cosine and sine functions, the final result for the displacement is exponential minus beta t factored out and oscillating factor, that is a linear combination of cosine omega prime t and sine omega prime t. We call this one to be the underdamped system. Underdamped. So damping, effect of damping make the amplitude decrease as time goes on, but still there is an oscillating factor, that is sinusoidal function. Again, as I told you before, omega prime is square root omega 0 squared minus beta squared. Omega prime is smaller than omega 0. That means the frequency decreases and oscillating factor has a smaller frequency. That means a longer period. The next case is overdamped case. Overdamped case. That means beta is greater than omega 0. If beta is greater than omega 0, the solution for lambda plus minus are like this. And because beta is greater than omega 0, the number inside the square root is a positive definite. That means we have no imaginary part, and lambda plus, both lambda plus and lambda minus are real numbers. And is the trial solution, the final solution for the linearly independent solution for the homogeneous equation is exponential square root beta squared minus omega 0 squared t and minus square root beta squared minus omega 0 t, except that there is a common factor exponential minus beta t. So the result is common factor e to the minus beta t and linear combination of exponential plus square root beta squared minus omega 0 squared t and minus exponential minus square root beta squared minus omega 0 squared t. We can recall the fact that cosine hyperbolic function is an average of exponential x and exponential minus x. This is an even function, and sine hyperbolic function is a difference of exponential x and exponential minus x divided by 2. By making use of these definitions, we can re-express two exponential terms in terms of cosine hyperbolic functions and sine hyperbolic function. This is very similar to the case for the exponential ix, exponential minus ix, sum 1 multiplied by 1/2 is cosine x, and exponential ix minus exponential minus ix divided by 2i is a sine x. So overdamped case has only the exponential term. Only the exponential term. Number C, if beta equals omega 0, that is mathematically the double root case, we already have written the solution, and the name of the physical name is critical damping. Critical damping. Okay, next we consider the driven damped harmonic oscillator. Driven damped harmonic oscillator is force equals minus kx. Harmonic oscillators of spring force, damping force minus bx dot, and driving force. Let me write just omega. Here, the notes, in the notes, we have written omega d. Newton's second law states that this is mx double dot. Thus, we have equation of motion mx double dot plus kx plus bx dot plus kx equals f0 cosine omega t. Let us divide both sides by m and make use of the definition beta equals b over 2m and omega 0 equals the square root k over m. And let us define force divided by mass is an acceleration, so a0. Define a0 to be f0 divided by m. Then equation of motion reduces into the form x double dot plus 2 beta x dot plus omega 0 squared x equals a0 cosine omega t. This is non-homogeneous. Second order linear differential equation. Okay. We know how to solve this problem. And this is just x equals x1, c1 x1 plus c2 x2, where x and x2 are linearly independent solutions for homogeneous equation. We divide it into three pieces. Omega 0 is greater than beta, underdamped. In that case, x of t was e to the minus beta t c1 cosine omega 0 t plus c2 omega prime t c2 sine omega prime t, and omega prime is the square root omega 0 squared minus beta squared. If beta is greater than omega 0, overdamped case, and the result was x of t equals e to the minus beta t c1 cosine hyperbolic beta square minus omega 0 t plus c2 sine hyperbolic beta square minus omega 0 square t. And the third case, beta equals omega 0, critical damping case. Critical damping case, x of t equals c1 plus c2t e to the minus beta t. And once you know the answer for the homogeneous equation, you combine this result to be x of t equals x particular solution plus x of t homogeneous. Let me call this one to be h. xht are these three cases for these three cases? Well, no. But the problem is that we have to determine what the particular solution is. There are many ways to find out the particular solution. First, we just make use of this right-hand side. Our trial solution is x equals a cosine omega t. Just a substitute. We can compute first order derivative minus a omega sine omega t, and x double dot is minus a omega squared cosine omega t. If we substitute these three results in the expression, we have a as an over factor, omega 0 squared minus omega squared cosine omega t, and we have minus 2 beta omega sine omega t equals a0 cosine omega t. Therefore, we have a mismatch. The problem is that this term is fine, but right-hand side cosine omega t, we have additional piece that is sine omega t. So, what we consider is just consider the phase. Just consider the phase. Just put plus 5, plus 5, plus 5. The reason is that if we add some sinusoidal functions, we have some, we end up with a single sinusoidal function. However, the phase is to be shifted. So, if I add this phi, everything, these relations are all fine, but except that what we have to do is omega 0, this is wrong. So omega 0 squared minus omega squared cosine omega t plus phi minus 2 beta omega sine omega t plus phi equals A0 cosine omega t. Alright, so here these two guys, we define, we factor this out. A square root omega 0 squared minus omega squared and this 2 beta omega squared, then multiplied by this is square root omega 0 minus omega squared cosine omega t plus phi minus 2 beta omega square root, same thing, sine omega t plus phi. And let's say this guy is cosine delta, and this guy is sine delta. Then we have A square root omega 0 squared minus omega squared plus 2 beta omega squared multiplied by cosine omega t plus phi cosine delta minus sine omega t plus phi sine delta, and A square root, same thing, cosine sine, that means cosine omega t plus phi plus delta. This one equals to A0 cosine omega t. Okay. So left hand side becomes right hand side if phi plus delta equals 0. That means phi equals minus delta. Therefore, our final result is this guy, and A amplitude times the square root, this guy is A0. So amplitude x particular solution is amplitude A cosine omega t plus delta plus phi, but phi is minus delta, and A is A0 over square root omega 0 squared minus omega squared plus 4 beta squared omega squared cosine omega t minus delta, where delta equals arctangent two beta omega 0 squared minus omega squared. That's our result. So once you find this particular solution, then you can add this particular solution to this homogeneous equation's general solution. You will find the general solution for this non-homogeneous equation. But it is rather complicated, and now let us introduce another method to solve this problem by making use of the exponential function. The reason why we had the complication in the previous case is coming from the fact that derivative of sine becomes cosine and derivative of cosine becomes a sine, and it flips the sign. In case we can make use of exponential function, the derivative has the same form except for the overall coefficient. So we notice that the equation of motion for driven damped harmonic oscillator has all coefficients real. Therefore, we can introduce a fictitious solution that is a complex function. Suppose that both wait a second. Cosine omega t equals real part of e to the I omega t. Sine omega t is the imaginary part of e to the I omega t. So this is a real part of e to the I omega t. What happens to the left-hand side? Just z double prime 2 beta z prime plus omega 0 squared z real part equals x double dot, because beta and omega 0 are all real, 2 beta x dot plus omega 0 squared x. What happens to the case we take the imaginary part? Then I would get y double dot 2 beta y dot plus omega 0 squared x y. Therefore, this one is related to this and this one is related to that. Haha. If I combine real and imaginary part all together, then I would say right, that's right. So this equation involves exponential function instead of cosine or sine. And sine or cosine can be projected out only after the calculation. At the end of the day, we take the real part or imaginary part to find out the right-hand side becomes cosine and the right-hand side becomes sine. Just the real part, take the real part for the cosine driving force and take the imaginary part to find out the solution for the sine omega t contribution for the driving force. So let us compute this. To find out the particular solution, we make use of similar manner, but we don't have to introduce any shift because exponential it is particular solution, then zp dot equals I omega t and zp double dot minus omega squared e to the I omega t. Everything has the same vector. So if I add these three pieces up, we do not have any phase vector. That's fine. So if I substitute these three into this complex equation, I find that omega 0 squared minus omega squared plus 2I beta omega e to the I omega t equals A0 e to the I omega t. Now, e to the I omega t are the same both sides. Therefore, if I introduce over factor alpha, then I end up with the final result that alpha equals omega 0 squared minus omega squared plus the 2I beta omega A0. That's it. So Z equals A0 omega 0 squared minus omega squared plus 2I beta omega e to the I omega t. Let's see. This one has an imaginary part in the denominator. We can rationalize the denominator. That can be done by introducing complex conjugate. Then our result is they have rationalized. So divide this one into two pieces. This is a complex number whose square is, whose absolute value is just 1. That means it can be written in an exponential form, like that, because of this negative sign. And delta is arctangent. Okay. As a result, our final result for the particular solution, A0 square root omega 0 squared minus omega squared plus 4 beta squared omega squared E minus I omega t minus delta. Then the value of x particular solution is the real part of z particular solution. That means A0 over and cosine omega t minus delta. Here again, delta equals arctangent 2 beta omega 0 squared minus omega squared. Let's compare this result with previous derivation. Our previous derivation using real analysis is A0 over square root omega 0 squared minus omega squared plus 4 beta squared omega squared cosine omega t minus delta, where delta is often the 2 beta omega squared minus omega 0 squared minus omega. They are exactly the same. So, in summary, we introduced a complex solution by replacing the sinusoidal contribution to the driving force with the general exponential e to the I omega t style. And then, after substituting the trial solution of e to the I omega t, we have exactly the same functional form, except that the overall factor has a constant containing imaginary part. And that is to be factored out as rationalized one multiplied by a complex number of unit magnitude. The complex number of unit magnitude is always expressed as exponential I something, and the minus delta is the shifted phase of the complex function. And the shifted phase is completely determined by the product of damping coefficient multiplied by the damping frequency, the driving frequency, divided by the characteristic frequency squared minus the driving frequency squared. Once the calculation is all done, particular solution, it has this factor and exponential form. When the driving force is a function of a cosine omega t, the final result is obtained by taking the real part of this complex function. If the driving force is a sine omega t, then the final result is obtained for the imaginary part of the z function. All three cases has the same phase shift delta, that is arctangent 2 beta omega over omega 0 squared minus omega d squared. We can make use of this result to find out the exact solution by imposing the initial conditions. Once the initial value for x0 and initial value for the position x0 and initial value for the velocity is determined as v0, then somehow homogeneous equation and particular solution contribute to acts as a general solution. So after imposing these results into the general solution, initial condition determines all those factors. You know, particular solution is completely determined except for completely determined with this phase shift term. This cosine omega t minus delta is given in here. Amplitude is completely determined. And then the first term is coming from the homogeneous equations general solution. These two values are to be substituted to find out the final result for the displacement. This is the case for the underdamped case, which has the oscillating factor as well as the damping factor. When the contribution of the when the system has a double solution, no double solution, but beta is greater than omega 0, we have overdamped system, and still the particular solution is the same as before, but homogeneous equation general solution are determined in a different manner. So these are the final result. And as a special case, we have critical damping of the case beta equals the omega 0. Then still we have the same particular solution. And damping factor. In all three cases, if t goes to infinity, this oscillating factor multiply damping factor, and this double root case damping factor only, this exponential beta t contribution, that is a homogeneous equation's general solution, absolutely vanishes as t goes to infinity in all three cases. So as t goes to infinity, only the particular solution survives in all three cases. So whether we have the three cases of beta equals omega 0 and the beta is greater than omega 0, or beta is smaller than omega 0. In all three cases, we have only the particular solution as t goes to infinity. In a similar manner, we can solve the problem for the sine omega t contribution for the driving force, and the results are given on the last page. As is stated there, as t goes to infinity, xh, the homogeneous equation general solution, vanishes because of the damping factor e to the minus beta t. Thank you.